I need to click one more button. The setup to go from Zoom to YouTube is not very straightforward. But now it's saying we are live. So welcome everyone. Thank you for joining us again for yet another installment of our guest speaker program. And before I get to today's talk, I would like to give a little bit of an intro of San Jose Astronomical Association. We are a very active astronomy club for amateur astronomers in San Jose here in the Bay Area. And I specifically mentioned here in the Bay Area now because this used to be an in-person event where we did not have any speakers from beyond Bay Area and or attendees for that matter. And that has changed with the pandemic, which is excellent. But we are trying to keep this going virtually and among some other programs that we are trying to do. So if you have any suggestions for us, please, you can find me on Meetup or on SJAA.net. I can put a link in the chat as well. I'm also one of the board of directors in the club. So feel free to reach out with any suggestions or any feedback that you might have, and or any questions you might have. Like we're happy to answer those as well. So without further ado, I'll talk about today's program and today's speaker a little bit. So Peter is joining us from George Mason University. He's a professor there. And he has done, I mean, I was just looking at his bio earlier and I was like, wow, that's some impressive research when it comes to exoplanets, which is a hot topic these days because we're all curious about what's beyond Earth and out there. He was actually principal investigator of NASA Earthfinder probe mission concept study, which is, I suppose he might share something from that today with us. And he has been a California resident before because that's where he earned his PhD at UCLA. And as I understand now, he's also a director of George Mason Observatories. So that's pretty cool. And I will have asked Peter to get started, and we are all very eager to listen about this topic. Peter, thank you.
Hi, well, thank you for having me. It's been quite an adventure to getting here. You know, and I'm an observational astronomer, and when I was younger, I had a real lack of a circadian rhythm, so I had no problem staying up late at night to observe the night sky from my upstate New York home. My senior year of high school when I bought a telescope, and my first telescope. And these days, now that I'm into my 40s, it's not as easy to stay up late. And so it's a little bit harder. And this is like way past my bedtime here on the East Coast at the hour of 11 p.m., which is somewhat ironic for an observational astronomer complaining about staying up at 11 p.m. But I did actually just catch a stomach bug yesterday from my one-year-old twins. And thankfully, my talk wasn't last night. Let's just say that. So today I'm here to, first of all, thanks for having me. And we have our own local astronomy club here in Northern Virginia in the greater DC area. We're about a half hour to an hour, depending on traffic, west of DC. And indeed, I did spend 18 years of my life in California, the Southern California, though, not Northern California. But I'm well aware of all the wonderful work that goes on in the Bay Area and San Jose in particular. Many of you might have a view of Lick Observatory on top of Mount Hamilton. And you're close to NASA Ames. And I imagine 10 years ago, you probably got a lot of talks about the Kepler mission. Well, a lot of the scientists that worked at NASA Ames and the Kepler mission came to NASA Goddard. I want to say a lot, a few, to work on the NASA test mission. So for those of you who have been a member of the club for a long time, you might remember some of those talks. So you can kind of think of this as a look at where we're at now in the search for other Earths. And give you I'm going to take a bit of an approach today that's a little unusual in the sense that I'm not just going to show a lot of slides with pictures on them. I'm actually going to try and do a little board work here with my iPad screen. And maybe give you some appreciation for a technically minded crowd of the challenges that we face going forward in the search for Earth 2.0. You can follow me on Twitter at Plavchan Peter. You can see my research group's webpage at exo.gmu.edu. So we do have a newsletter at our observatory. We are the largest on-campus observatory in the Mid-Atlantic states. We're not quite as big as Lick Observatory with our 3-meter telescope, but we do have a 1-meter telescope on campus. And it's a wonderful telescope. We have our own public nights. And so we do have a newsletter and occasionally put out science articles and, kind of night sky articles. Like our April edition isn't out yet. And I know it's April 9th now. Better get to that. But we're going to have an article on the International Dark Sky Week, for example, which is coming up later this month. So in the 2040s, NASA's going to launch a mission, or hoping to launch a mission, that is going to take the first pictures of another Earth-sized world. And perhaps with the easiest approach for finding other worlds, which is at least conceptually to understand, imaging them. Now this is some aerospace company's animation of what this telescope concept might look like. And I'm going to probably skip ahead in the video if I can here. Well, maybe not. It's not letting me. We'll watch it for a little bit longer. But NASA's hoping to launch a mission. And the fairing's going to fall away here soon. There we go. And there's the telescope inside. We have a bigger version of the JWST telescope, which just launched this past December. And it's hoping to take a picture like this. And this is a simulated image of what our solar system
I'm just going to jump
like
in.
if it was at a distance of around 10 parsecs or 33 light years, with the light from our sun blocked out to see the faint glow of Earth, Venus, and Jupiter next to our bright sun. And the lines of their orbits here are drawn on, you don't get nature doesn't show you the orbits of the planets, you'll just see the faint fuzzy blobs. But there are a lot of unanswered questions we have as we look forward to such a mission in a couple of decades, which is if we want to image an Earth-like world and see a pale blue dot around another sun-like star, how many stars do we need to look at? And how big and expensive does this telescope need to be? And more importantly, I guess not as important, but also important, will we know where and when to look? Will we be able to tell the difference between a Venus and Earth, for example, and completely different habitability outcomes? So in order to dive in, I should back up a second and tell you about what an exoplanet is. So an exoplanet is a planet that goes around another star. And you may have seen in the news on CNN within the past week, the announcement that NASA has discovered or validated over 5,000 worlds, exoplanets that orbit stars other than our sun. And I like to characterize what we do as discovering new worlds. And it's kind of an exciting time to be alive, that those first 5,000 have happened in the past 30 years. This is just an artist's rendition of one particular planetary system, 55 Cancri E, the fourth planet in a 4-planet system. That's this one. Its orbital period is less than 1 day, so its year lasts less than 1 day, and it's so hot it's getting blasted away by radiation from the star, and the surface is molten. So we have over 5,000 of these known today. What do we know about them? And what have we learned about these other worlds and the diversity of exoplanets in our universe? This is a plot of what we call the mass period distribution of exoplanets. Now the x-axis here is a logarithmic scale showing the orbital periods of the planets, and the y-axis here is either an approximation or a measurement of the masses of those worlds. And the colors of these worlds are refer to the detection methods by which they were found. And so you'll notice some patterns here. There's some clumps, and let's see if I can draw. Oh, there we go. Let me back up a second. Sorry, let's go back. Let's see if I can annotate. There we go. Yeah. All right, so you can see that we have some different clumps here. And you see some patterns emerging. You have a little bit of a tail here, and that's all the direct imaging exoplanets that we found to date. But the majority of the planets that you can see right away are discovered with the Doppler method, the radial velocity method, and the transit method. I'm going to tell you about each of those in turn. But we've learned a lot of things about our universe. We have populations of hot Jupiters, planets about the mass of Jupiter. The mass here is in Jupiter masses. And so these things are worlds the size of Jupiter. But Jupiter, if we were to put it on this chart, has an orbital period of 5 days, which is on the order of 2,000 days. Would be all the way out here. So many of these orbit closer to their star than our own Jupiter does, although we have a bunch found with direct imaging that orbit much further away. And then we have a gap in the middle, kind of a lack of warm Jupiters. And then we have this other gap here between the Jovian worlds and the Neptune and terrestrial sized worlds. And if I were to put the Earth on this chart, the Earth is very lonely down here in an orbital period of 365 days, and a mass of 1,000th of Jupiter. Sorry, 1/300th the mass of Jupiter. And you might ask yourself why, why the Earth is so lonely in this diagram of over 5,000 discovered worlds. And the answer has to do with how we find them. And so I'd like to tell you a little bit about why finding these worlds are so challenging, why our discoveries are dominated by these hot Jupiters and these cold Jupiters and these planets, unlike anything in our solar system, these super Neptunes and super Earths that are, we have nothing in between the mass of Saturn, which is right about here, and the mass of Neptune, which I forget exactly where it is, but it's around here. And we have in our universe a lot of worlds in this range here that are unlike anything in our own solar system. Of course, hot Jupiters themselves, the orbit of Mercury is in here, and we have no planets inside this region in our own solar system. So how is our universe populated with a ton of short orbital period compact planetary systems, unlike anything in our solar system? So in the search for Earth 2.0, we found a huge number of mysteries. And I'm not going to spend a lot of time today talking about these other classes of planets, but just to let you know that they're there and that they've been stepping stones on our way to this search for other Earth-like worlds. And then also as a means by which to understand why we've kind of hit a sensitivity limit with the transit method and the Doppler method, trying to push down towards true Earth-like planets. And feel free to ask any questions in the chat. And I'm going to kind of do this like a little mini lecture, and we'll see. We'll have fun with it tonight. All right. So let's start first with the direct imaging method, which is probably conceptually the most easiest to understand type way of searching for planets around other worlds. This is a video of the, let's replay it, of the Beta Pictoris system, which is one of the brightest stars in the sky, as many of you may know. And in the 1980s, we knew that it had a disk of debris around it, indicating that it was very young and undergoing the process of planet formation. So with something called coronography, which I'll talk about in a minute, blocking out the light from the star, we were able to see the disk around that star. And in 2003, we saw a small blob that 2 years later disappeared. And then in 2009, reappeared on the other side. And so this was not the first, but one of the first discoveries of a directly imaged planet around another world. Now this one, the separation, if I remember correctly, is around 8 times the distance from the Earth to the Sun. Actually, I might be wrong about that, but don't quote me on that. But it's at a similar distance to the Jovian planets in our own solar system from the Sun, and it's a super Jupiter. So the direct imaging method requires blocking out the light from the star, and this is one of the videos made about a decade ago. And this is one of the best videos we've taken of another world. And this was from about 7 years ago. This video was made. I'll watch it one more time. Here it is. And so 2009, 2010, and 11, and then it disappeared behind the star again, which has been blocked out there on the left. After the discovery of this world, a set of 4 planets was found orbiting the star HR 8799, which is another young, hot, luminous star, like Beta Pictoris. And B was found first, which is out over here. And I'm just going to circle them, then C, then D, and then E was the last world that was found. And over time, they were able to see something amazing. The planets moved in their orbits around the star. So the direct imaging method is definitely the future, which is why NASA is launching, I'll play that animation one more time. This is why NASA is launching a mission in the 2040s to image other Earth-like worlds. We know it works. And these are images taken from the ground, so when we go to space, we'll do a lot better. Let's see if it'll let me play it one more time. Apparently not. There we go. But these are Jovian worlds. So this is like a scaled up version of our own solar system. It's really amazing to see this, though. It's like Kepler's laws in motion around another star. It's the first time we've ever seen anything like that, where you see the direct light from the planets themselves. But you just see here that they're blocking out the light from the star to see these faint glow. And these planets are 5 to 10 times the mass of Jupiter. They're enormous, and their separations are quite large too, much bigger, 3 to 4 times further away than the Jovian planets in our own solar system. And they're young. They're young enough that, and a few hundred million years old is pretty young by celestial standards compared to our sun's age of 5 billion years. They're young enough that we can see the heat from the planets themselves left over from their formation. They're still cooling, and that makes them easier to detect. So I wanted to talk a little bit about the challenges of direct imaging and why it's such a hard problem. If I imagine I have a star, and it's emitting some amount of flux in all directions, and I just want to understand how much of that flux is an Earth-like world, 1 astronomical unit, or about 150 million kilometers away from that star. How much of that flux is it going to intercept? And it's easy to assume geometrically that this flux from the star is going to be spread around in a sphere with a radius of, okay, hold on. Let's see this. Let me switch easily to eraser. Yeah, it does. Let's go to eraser mode. All right, well, I'll scribble it out. Times 1 AU squared, which is the surface area of the sphere of light coming out from the sun as it reaches the Earth. And the Earth is only going to intercept roughly pi times the radius of the Earth squared amount of that light. And so if we want to ask the question, what's the ratio of light from an Earth-like world compared to a sun-like world that an Earth-like world would reflect to a distant observer observing our solar system? It would be roughly this equation, 1AU here, assuming it was a perfect mirror. So it can only get worse. So if you imagine the Earth was a perfect mirror and it was reflecting a fraction of the light from the star back towards us, and we're seeing that planet in reflected light, and you do the math, the number is around 4 times 10 to the minus 10. And after you correct for the fact that the Earth isn't a perfect mirror, at visible and near-infrared wavelengths, it's around 10 to the minus 10. And that means that for every 1 photon of light we get from an Earth-like world orbiting a sun-like star, we get 10 billion photons from the star. That is a proverbial needle in a haystack. And that is the challenge of the direct imaging method, you have to be able to remove all of that starlight and correct for it to better than 0.1 parts per billion in order to hope to be sensitive enough to see an Earth-sized world. And that's why we haven't done it yet. The current limit of sensitivity is around 10 to the minus 6 from the ground. There are some instruments like on the Keck Observatory and Gemini Observatory and VLT in Chile that are able to reach those types of sensitivities. So we have 4 orders of magnitude to go. And NASA is going to launch the Roman Space Telescope, which has some technology that's going to hope to get us down to 10 to the minus 8 in sensitivity. So another factor of 100 from where we are today. So that's the challenge we face in order to see a pale blue dot around another sun-like world by the time I retire. Right? That's the image I showed you at the beginning of my talk. Is something I'd like to see at the end of my career. So how do we surmount such a difficult challenge? There are 3 different things we could do, one of which is hardware. And so back a century ago, Bernard Lyot invented something called the Lyot stop to look at the sun and see the sun's corona. Another example of seeing something very faint next to something very bright. Many of you may have seen the Great American Eclipse a few years ago. We got another one coming up in 2024. And Lyot was interested in creating an artificial eclipse of the sun with a telescope in order to see the faint corona next to the sun. And this was the technology he came up with. So if you imagine you have light from a telescope coming in, and you put a physical disk in the image, blocking out most of the light from the star, that wasn't enough to do it. He also then did some optical trickery to put a second stop in what's called the focal plane of the optics. Again, even better sensitivity with a coronagraph where only 1.5% of the original starlight is let through, while still letting through all the other starlight from a nearby planet. So this is now a technique that's almost a century old. And the light from a nearby planet, or in this case, the corona, when he came up with this technique of the sun, would miss this physical stop, but would still make it through this stop in the optical path, and then be able to increase the contrast ratio in hardware. The second piece of hardware advances that people have worked on in improving our sensitivity to starlight, because this only gets us a factor of 100, right? So this only gets us down to 10 to the minus 2. And we still got to get to 10 to the minus 4, and then where we're at today at 10 to the minus 6, and then 10 to the minus 8, and then finally 10 to the minus 10 to see another pale blue dot. So we need something else. And the second technique that got invented, which I don't have any fancy slides on, is adaptive optics imaging. And from the ground, we use that to correct for the blurring effects of the Earth's atmosphere, and hence the slide comes from the center of adaptive optics, which is right there in the Bay Area at Santa Cruz. I imagine you've had some speakers from Santa Cruz in the past as well, maybe telling you about adaptive optics, but adaptive optics got their start at Lick Observatory in the 1990s, when the technology behind it became declassified. So at least the public start, actually that's not even true. The public start of adaptive optic systems was a theory, which was invented by Freeman Dyson, who, if you've heard of not Dyson vacuum cleaners, but Dyson spheres, and like the search for extraterrestrial intelligence, that Dyson, he invented the theory of correcting for the blurring effects of the Earth's atmosphere. No one believed him that it could be built at the time, except for the US military. The US military had the same problem astronomers do. We look up through the blurry Earth's atmosphere. The spy satellites need to look down through the blurry Earth's atmosphere. So 1980 Star Wars Reagan initiative was partially funded in order to make adaptive optics work. And they did. They made it work. The technology being classified in the 1990s. And they built the first adaptive optics system on Lick Observatory in San Jose in the late 1990s. And today, the rest is history. Every major telescope in the world has an adaptive optics system. So here's an example of what that looks like. This is a real example from my colleague, Thane, taken in July 2005 using Keck Observatory, the largest optical telescope in the world. It's got a coronagraph blocking out the light from the star, but and it's got an adaptive optics system correcting for the blurring effects of the star, but you still see a ton of light scattered from the star. You might ask yourself, why isn't all that light gone? So this is now getting us, with adaptive optics, we're getting down to the 10 to the minus 4 level in contrast, but still not enough. And this adaptive, this scattered light, as we call it speckles. And this has to do with imperfect corrections in optics and imperfect corrections to the blurring effects of the Earth's atmosphere, where not quite all the light gets put behind this LEO coronagraph and brought into what we call the diffraction core. And so the rest of the trick was actually software. So the software got us from 10 to the minus 4 to 10 to the minus 6, another factor of 100 in gain. And we have a question in the chat. And just to answer the question from Alan, since the LEO coronagraph is sensitive to dust and optics, does it work better above the atmosphere? Absolutely. So yeah, it's just more expensive to put satellites into space. Yeah, technically, according to the general public, I don't believe there's ever been an adaptive optics system that has flown in space. That being said, the JWST telescope has active optics, but not quite what we're calling adaptive optics. Adaptive optics, I have an animation. Maybe I could show it real quick. I'll save it maybe for the end of the talk if we have time. In any event, it does correct for the twinkle of the Earth's atmosphere. The last bit is software. And so interestingly enough, no matter what star anyone looked at with adaptive optics, with a coronagraph, with a high contrast imaging observatory trying to see the faint light of a planet next to the star, they all looked the same, and they were all related to the shape of the optics. And so they just developed methods to subtract off the extra light. I mean, it's really just an advanced algorithm of subtraction. And the state-of-the-art algorithms are called advanced loci, which stands for locally optimized contrast, high contrast imaging, or something like that. But it's basically subtraction of pieces of the image around the image, where they're subtracting it off using a model of libraries. And in this particular case, this is the discovery of 51 Area B. And we still have the light from the star not perfectly corrected, but we have the discovery of a Jovian planet just beyond around this star 51 Area, just beyond what would be the orbit of Saturn in our own solar system. So that's where we're at with the direct imaging method today. And as I mentioned, the Roman Space Telescope will hopefully launch later this decade, and will push the boundary of what we could do by taking some of these same techniques that have been developed over the past couple of decades and applying them in space. And a lot of it has to do, as I talked about, the imperfections in the optics. So one of the things you have to do is you have to control the shape of your mirrors to an accuracy well within a fraction of a wavelength of light. And we do believe we have the technology to do that. And so it's just a matter of flying the dang thing and building it. And hopefully that gets done before I retire. So now I want to shift gears a little bit and talk about the most successful method for finding planets around other stars, and talk about whether or not we've been able to use that to find an Earth 2.0, which is the transit method. The transit method has been used to find the majority, I don't know if it's the majority, but the number one method for finding planets around other stars. And it's also a fairly simple method to conceptually understand. When a planet passes in front of the star with respect to our line of sight, it blocks light from the star. What might be a little bit harder to understand is And I move this, I lost a slide here. Let me skip ahead for a second, I'll come back. Yeah, so actually if we go to this one right here, to conceptually understand the transit method, you have a star, which you're not seeing with your telescope. You don't resolve the surface of the star. Even with the biggest single dish telescopes in the world, the surfaces of stars are not resolved. It requires a technique called interferometry to resolve the surface of some of the nearest biggest stars, which has been done for a few hundred stars. But with single telescopes, and particularly with the transit method, we're not resolving the surface of the star. But when you have a planet passing in front of a star, the amount of light it blocks to first order is just a ratio of areas of circles. So you have pi times the radius of the planet squared for the area of one circle divided by pi times the radius of the star squared. And so the pi's cancel, and you just have RP over R star squared equal to the change in brightness of the star due to the planet blocking the light from the star. Now, this is under the approximation and assumption that the star isn't doing anything. Its surface is, in fact, active, however, with spots and flares and plages. And of course, we also have noise in the signal we're trying to measure. And so that limits our sensitivity as well. But there are various quantities we can measure with the transit method. And as some of you may know, in 2009, run out of NASA Ames, the Kepler mission was launched to stare at over 150,000 stars, and it detected over 1,000 planets as small as Mercury with over 5,000 candidates. Going back to this example here, I want to plug in some numbers to tell you an idea of what this value is. So the radius of Jupiter is approximately 1/10 of the radius of the sun. So that means the change in brightness for a Jupiter-sized planet passing from a sun-like star is only 1%. And the radius of Earth is about 1/100th the radius of the sun. And so the change in brightness of an Earth-like world passing in front of a sun-like star is about 0.01% or 100 parts per million. So in order to detect an Earth-sized world around or transiting a sun-like star, you're going to need an ability to detect changes in brightness of 100 parts per million, and preferably your noise level has to be 10 times better than that. And we can do that today. With the transit method, we can detect changes in brightness with space-based facilities of about 10 parts per million. This actually shows the first discovery of a transiting planet in 1999. This was a Jovian-sized world, and its change in brightness around its star was around 2%. Number one, the planet was a little bit bigger, and I think the star might have been, I think the planet was just a little bit puffier. This was the first discovery in 1999, and it was easier. That's why. So when we think back to that chart I showed you earlier of the plots of planets around other stars, we found a lot of Jovian worlds with the transit method first, primarily just because it was easier with the sensitivity of the technique. Today, the Kepler mission is gone, but we do have the NASA test mission. And it is searching for Earth-sized worlds around smaller stars. If you think back to the animation that I showed you, or sorry, the diagram I showed you, if you make the star smaller, or in other words, if you choose smaller stars to look at, you can detect smaller planets with the same amount of precision sensitivity. So after the Kepler mission, that was something we realized was a low-hanging fruit.
Tests.
What we call the
Transiting
opportunity
exoplanet survey satellite.
to find Earth-like worlds. Sure, we could
Discovering
find
new
a
Earths
few
and
Earth-sized
super-Earths
worlds
in the solar
orbiting sun-like
neighborhood.
stars with the Kepler mission, but for reasons I'll explain in a little bit, they were hard to find in the habitable zone. The habitable zone being about 1 AU from a sun-like star. But if you go to a smaller star, not only were the signals bigger and easier to detect, but the habitable zones were closer in because the stars were cooler. And so you could see the transits more often. And so the test mission used 4 cameras, each one of them covering 4 times the field of view of the Kepler mission. to step and stare 27
TESS
days
has a
at
simple
a time
stare and step observation
over
strategy.
strips of the sky, eventually over the course of a year, mapping out half of the sky.
TESS points anti-solar
This is
and remains
animation
fixed
showing
in
its
inertial
pointing, and the
space
Kepler
for
mission now, I
27
believe,
days
has been
or
in
2
orbit now
orbits.
for at least 4 years. I think it's started into its 5th year now. And it's mapped the northern and southern hemispheres
TESS is
twice.
a 2-year all-sky survey mission with
and I've been
26
heavily involved
observation
in the
sectors,
NASA TESS
or
mission.
13
The NASA
sectors
Kepler
per
mission
year.
a little bit less of an extent. And it too has now
The
found
overlap
over
of the
5,000
observation
candidate
sectors near the
worlds,
pole is
around
optimized for
other stars.
JWST's
And by
continuous viewing
looking
zone.
around the whole sky,
After completing the
you
northern
could also
hemisphere in
find
year
worlds
1,
around
TESS
stars that were
transitions to
closer,
map the southern
brighter,
hemisphere in year 2.
easier to follow up and easier to characterize. The Kepler mission stared at 150,000 stars very deep in the constellations of Cygnus and Lyra, because even though its field of view at the time was revolutionary, those stars were still relatively faint compared to what the NASA TESS mission does, making many of those candidates very challenging to follow up and characterize those other worlds. So the NASA TESS mission also took advantage of one other key discovery from the Kepler mission, was that not only are cooler worlds likely to be easier to find Earth-like worlds, we also learned from the Kepler mission that those worlds were more common at short orbital periods than they are for Sun-like stars. So Kepler found for us that there are tons of compact multi-planet systems orbiting interior to what would be the orbit of Mercury. It's actually an area of active debate right now, which is how did those planetary systems form? Because we have nothing like it in our solar system. And perhaps one of the greatest examples of that discovered within the last 10 years is the TRAPPIST-1 system that many of you might have heard about in the news, which took this M-dwarf opportunity to the extreme. Now, the TRAPPIST-1 system was not discovered with Kepler, and although it was eventually looked at with Kepler, and it was not discovered by the TESS mission. It was actually discovered with a ground-based telescope, so in Europe. And so some astronomers realized that if I went to the smallest stars possible, I might get lucky and find a set of transiting planet systems. And they got lucky in one of the first stars that they checked. And they found this system of 7 Earth-sized worlds, potentially 3 of which orbit in the habitable zones of that star. But since that star is at the coolest end of what a star can be made of, its habitable zone is super close in. And you can see how it is per scale here compared to our own solar system on the bottom. Now, we haven't found many other systems like this one. The TRAPPIST-1 system looks like it's fairly unique. And people have tried and looking for and discovering other TRAPPIST-1-like systems around the coolest, smallest stars where Earth-like worlds produce a signal that's big enough to detect from the ground. It turns out that we kind of got lucky with this one. And then the other thing I want to say about this particular system was that its scale is actually more appropriate to be compared to Jupiter and its moons of Io, Europa, Callisto, and Ganymede, rather than, say, our own solar system. It's more like a massive Jupiter system than it is more like a mini solar system. So we learned a lot of other things with the transit method besides just the radius of the planet. But we also get information when the planet passes behind the star. And we could also do some atmospheric dynamics. So if this planet has an atmosphere around it, then we can look for changes in brightness as a function of wavelength because of quantum mechanics. At different wavelengths, the atmosphere will switch from becoming transparent and opaque if it's not cloudy or hazy. And as you can imagine, the equation for predicting a change in brightness for the detection of the planet itself goes as the ratio of the radius of the planet to the radius of the star squared. The atmosphere is just a thin little shell on top of the solid planet in the case of a terrestrial world. So the effect is even smaller by another factor of 100. So just to put things in perspective, the transit of an Earth-like world in front of a sun-like star is 100 parts per million. And then to understand something about the atmosphere of that world, we want to look for changes in that 100 parts per million. So if you shrink the size of your star, it does become an easier problem, but it's still a really challenging measurement to make because you're limited by the precision with which you could measure the brightness of that star with everything it has going on its surface. Nonetheless, we're going to try with JWST, the space telescope that is launching, and it's going to look at the TRAPPIST-1 planets, and it's going to look at the some other worlds that have been found by the NASA TESS mission to characterize their atmospheres. So the way they characterize their atmospheres, they look for change in transit depth, change in the amount of light being blocked as a function of wavelength or color. And that gives us information about what the atmosphere is made of as a function of wavelength. And they're going to try it. And we might get lucky. So some of the first Earth-like worlds are going to have their atmospheres measured with JWST. And they're going to try and measure changes in brightness of 3 parts per million. That's their goal. Don't know if we'll get there. It'll be really interesting to find out over the next 10 years. In order to potentially constrain the atmospheres of an Earth-like world. And if we get lucky, we might detect a biosignature in the atmosphere from something like oxygen, which is a highly reactive gas, and so has to be replenished in the atmosphere. The last thing I want to talk about is why haven't we found a lot of Earth-like worlds with the transit method around sun-like stars? And the answer is, when we go back to this diagram here, you have to have the right inclination of the orbit. The planet has to pass in front of the star with respect to our viewing angle. And if you change that angle by only a degree, or even in the case 0.1 degrees for an Earth-like world around the sun-like star, it just won't transit anymore. And that's why Kepler had to look at 150,000 stars to find the number of transiting planets that it did. So this is a plot that shows the transit probability that if we were viewing our own solar system from far away, that given some random orientation of that planetary system's plane of planets, what would be the probability that that planet would transit in the first place? And for an Earth-like world, is 0.5%. So only 0.5% of stars have the right inclination that it would transit if we were looking at it from afar. So that's why, and then you have to multiply that by how many stars have Earth-like worlds. Whoops. And you might say that number is around 10%. So now you're looking at 0.05%. So that means you have to look at 2,000 worlds to see one of these. And Kepler looked at 150,000. So where are they? Why didn't we see a lot more Earth-like worlds, on the order of 75? Well, again, it has to do with sensitivity and detection efficiency because those transits only occur once a year for a sun-like planet. And we have a beautiful question in the chat, a couple of questions. If a planet is moving from a star, it also has a moon rotating around it, like our own double planet system. Will you notice the fluctuation as a dip in flux in your flux data? The answer is yes. And there has been a search in the Kepler data for moons. And interestingly enough, for dynamical reasons, we don't expect planetary systems very close to their stars to be able to dynamically hold on to their moons. So you automatically have to go far out from the star to have enough space dynamically for the survival of a moon, so it doesn't get disrupted by some of these other planets, dynamically. And we've looked, and there is one system, I forget the name of it exactly, but there has been the detection of a potential exo moon, and it hasn't been confirmed yet. And so that's what we're working on confirming, but it turns out it's very hard because it's a moving target. So you can't always predict when the transit of the moon is going to happen, and it's different every time because you don't know the orbital period of the moon. And it's also an incredibly small signal. But people are looking and people are trying, but we don't have any confirmed exomoons to date. So the other challenge is in the data, and we're really working in noise. And so if you're looking for a 1-year signal, something that happens once a year, it's low probability, and it's hard to see. There might be only 4 of them in 4 years, if you get lucky and avoid all the data gaps. Now, the TESS mission has been able to find some of these worlds orbiting M stars because their orbital periods are shorter. That's why each sector stare was only 27 days. And so it has found a few. I think it's around 6 candidate systems. They've been very hard to follow. One of them has been confirmed, or validated anyway, TOI 700D. It's a habitable zone Earth-sized world orbiting an M-dwarf star. But some of them are just a little bit challenging to follow up. And so this is for systems where the star's temperature, the surface temperature is less than 4,000 Kelvin, which makes it an M-dwarf. And for planets that have a radius less than twice the radius of the Earth. We used to have a lot of worlds that have been discovered by TESS in the 2 to 4 Earth radius range. We now know that those are not terrestrial, by and large. They're more likely to be mini Neptunes. We have since discovered there is actually a real difference in populations of exoplanets. And so for truly likely terrestrial worlds, there's actually not that many that the TESS mission has found. Oh, and this was for 6 candidates where the amount of flux they receive is less than twice the amount of flux that Earth receives from the sun. So, they're still pretty hot, but and then we had a question from in the chat. Conch, hi Conch, asked, can JWST do a better job of finding exoplanets with transit orbits not lining up with Earth using infrared signature? So the answer is no. The JWST is not going to be a discovery mission for exoplanets, and the reason has to do with the field of view, because you have to look at a large swath of the sky, and the TESS mission was designed exactly to do that. JWST's field of views are tiny. And so it's targeted. It's looking at individual targets in the source field of the sky because it's got a big primary mirror, and it's got a relatively small field of view. So it's not going to be able to survey lots of stars. But once you know that the planet is there, it will be excellent for characterizing that planetary system. Of course, in fun facts, JWST takes an hour for it to change its pointing, to move from one target to the next, because it is a size of a tennis court. And all the mechanics need to settle down, and the vibrations need to settle down after it turns. Point being that the targets for JWST are chosen very carefully. It's a $10 billion mission, lasting about 10 years. So you can imagine the cost of this mission is about $1 billion per year. So even if there were 1,000 days per year, which of course they're not, but every 8 hours of JWST telescope time costs about $1 million in taxpayer dollars, effectively. And so thinking about things that way, $1 million for 8 hours of time, which, some of these transits, by the way, they last, anywhere from half an hour all the way up to 8 hours, typical numbers you might see. And so you need a lot of telescope time. And so these are $1 million observations that we're talking about when we're collecting this data to characterize the atmosphere of another world. So each target is chosen really carefully. So that's the transit method, and I realize I'm going way slower than I thought it would be because I'm taking some time to show you some math. I want to tell you a little bit about another method, which is one I use a lot, which is the Doppler method to find other worlds. And it relies on, this is the second most successful method for finding exoplanets to date. It relies on Newton's third law, which is for every action, there is an equal and opposite reaction. planets don't orbit the sun in our solar system, common to what you might learn in elementary school. That approximation is good enough, but they actually orbit the center of mass of the solar system. And what that means is that the sun does too. The sun has an orbit. It wobbles in response to the planets going around it. In this simple toy model, this is exaggerated here, but the star does orbit as well as the planet, and they orbit a common empty point in space. And as a result of that, as you're watching the star, as shown, oops, sorry, trying to get this animation to play again. There we go. We're over here watching, and so as the star is going away from us here, the light from the star is shifting to the red, and when the star is moving towards us, the light from the star is shifting to the blue. And this is the Doppler effect, red shift and blue shift of the spectrum of the star, shown as a cartoon here. These black lines, these are not some arbitrary barcode. This is the barcode of quantum mechanics. At every specific wavelength here, there's a particular atom in the atmosphere of the star, with electrons in it, and those electrons are jumping up in energy level. And in order to do that, they absorb a photon at that specific wavelength equal to the energy gap between those two energy levels in that atom, causing an absence of light at that wavelength. And this happens for a variety of different atoms and a variety of different electron energy level and electron energy transitions in those atoms, producing a barcode of missing light in the rainbow or spectrum of the star. And because of the Doppler effect, we see that barcode shift back and forth, and we can measure it. And so we can watch, shown in this animation here, basically the same thing. We can measure the speed of the star now towards the observers down here. We're down here. And this is the edge-on view if it was transiting down here. But we can watch the speed of the star towards or away from us as a function of time. And the amplitude by which that signal changes, combined with the orbital, how often it repeats, tells us the mass and the orbital period of the planet. So the transit method gives us the radius of the planet. The Doppler method gives us the mass of the planet. And so with those two things combined, we can get the density, the bulk density of that world. To talk about the Doppler method, and I'm going to skip to the end here. As I mentioned, it's a seesaw thing. So we have the star on one end of the seesaw. This is the center of mass. And then we have the planet on the other. And it's a balance point gravitationally, so that the mass of the star times the distance, which I'll just give the letter A, from the star to this fulcrum point, the center of mass, is going to equal to the mass of the planet times this distance here from the fulcrum to the center of mass to the planet's location. And these are just what we call in astronomy the semi-major axis, or orbital radius if it's a circular orbit. And so if we have a planet going around a star, it's going to have some distance a star here. It's going to have some distance AP. And it's going to take some time t, or some orbital period p. We can go through the math, and we know that as the star wobbles around, it covers a distance 2 pi a star in some time p, and that's the velocity of the star. And so we can measure the velocity of the star, the average velocity of the star for a circular orbit. We can measure the orbital period of the planet. And then from this information, we can solve for this, a star, which we can plug into here. And we can estimate the mass of the star. And then this, we know from Kepler's third law that the orbital period squared is equal to a sub p cubed over the total mass of the system, which is m star plus mass of the planet. And so we can use this information to solve for the mass of the planet in a nutshell. That's, for those of you that like working with equations, that's what we do. Now that's the simplest approach to it. This is the more actual way we measure the mass of the planet using math. But this is for those of you that are curious, this is the full equation for the z position towards or away from us for an orbit that's eccentric and at some arbitrary inclination. For those of you that are familiar with calculus, you take the time derivative of that to get the velocity of the star towards or away from you. And this is eccentricity. This is the orientation of the ellipse. And you can then simplify that or just rewrite it with this thing k, and this k here has that 2 pi a over p that I was talking about right here. So this is just equal to k for a circular orbit. So this is the more complex version of what I just showed for you there, but we do it, and we can basically write down an equation down here where if we measure the velocity of the star, the orbital period of the star's wobble, and we estimate the mass of the star, then we know the mass of the planet. And that's the beauty of the Doppler techniques. It's indirect. You don't see the planet, but you do get the mass of the planet, which is important. It turns out if you don't know the mass of the planet, you may not know whether it's rocky or terrestrial. So even in the 2040s, when we go and directly image these pale blue dots around other sun-like stars, even if we're able to figure out the orbital period of the planet by watching that planet over multiple times over the course of a year with that space mission, we're still going to want to measure the velocity of the star to get an estimate of the mass of the star. This was the first world discovered with the Doppler method in 1995, 51 Pegasi b. This is the velocity of the star as a function of time, and it's changing by 100 meters per second. It's quite a bit for an Earth-like world in a habitable zone orbit. The change in velocity that we hope to detect is 10 centimeters per second. And that is equivalent to turtle speeds. The current state of the art is 1 meters per second, which is basically a slow jogging speed. So we can detect with today's technology the motions of stars in response to their orbiting planets. Stars that are 300,000 times the mass of the Earth with all their activity on the stellar surface, moving back and forth at jogging speeds. Might blow your mind a little bit. So the direct imaging method, 10 to the minus 10 contrast, we're at 10 to the minus 6. The transit method, changes in brightness of 100 parts per million, and we're at 10 parts per million, and we're hoping to get to 3 parts per million. The Doppler method, we can now detect changes in velocity of 1 meter per second, but we're hoping to get to 10 centimeters per second to detect Earth-like worlds. Hopefully I'm convincing you that these are hard problems, and these require precise measurements. And exoplanet astronomy is really a precision astronomy in the push towards the sensitivity to detect Earth-like worlds. And in the interest in time, and how much time do we have, Sukata?
Let me unmute myself. Yeah, I mean, you can go on.
You're muted. Oh, wait, I can't hear you. Hold on.
Oh, wait.
Sorry, go ahead.
Oh, I was saying we can take another 5 minutes or so, and then just have some more time for Q&A, if that's good.
Okay, great. So we can do that, and I'll skip over a few things, but it's a hard problem. This is one of the 4 world's leading spectrometers to measure the velocities of stars. This is the 4-telescope VLT spectrometer Espresso in Chile, and it's inside a vacuum chamber. And in order to measure these 10 centimeter per second velocity changes, the spectrograph has to be stabilized in pressure and temperature to exquisite levels. We're talking millikelvin, 1/1000th of a Celsius. And very stabilized, and they put it room inside of a room inside of a room to keep everything controlled. And we can do that. So we've been working on pushing the Doppler method technique, but we ran into a problem in the year 2010 where the sensitivity stopped falling off. And this is a plot of showing the discovery of the number of Doppler worlds. And in the last decade, we stopped being able to find other worlds. And the challenge, as it turns out, is activity on the surface of the star. When you have spots and flares on the surface of the star and Plavchans and other active regions, the star spins. The star is not a blank sphere. These active regions rotate into and out of field of view, causing false Doppler signals. In fact, one of the first worlds we found that we thought might be a habitable Earth-like world, Gliese 581d, turned out to be at an orbital period equal to the stellar rotation period of the star. So the Doppler method has also been foiled in its attempt to find Earth-like worlds. And so the transit method has been foiled because it's a low probability occurrence. The direct imaging method has been foiled because we don't have the sensitivity yet. And so we haven't found any true Earth twins yet to date, but we're still working on it. And as a case in point, I want to talk about a few projects I'm involved in now. We've been using a spectrometer in Hawaii, shown here, on the IRTF telescope, where we have the Doppler sensitivity at near-infrared wavelengths to detect Earth-sized worlds around M-dwarf stars. And the reason for that is this is a visible light image of the sun, and these active regions appear very dark. Of course, they're not completely black, but as you go from visible light to near-infrared light, they get harder to see. So at near-infrared wavelengths, we are less sensitive to activity on the surface of the star. And I actually used that. We found a planet system orbiting the young M-dwarf star Au-Mc, which is the second closest pre-main sequence star to the sun. It's a well-known system because it has an edge-on disk of debris. So it's a young system, and that debris is moving in that disk. And with the first sector of the test mission data, we found a Neptune-sized planet transiting in front of that star at an orbital period of 8.46 days. And we confirmed it with the Spitzer Space Telescope. And this is the cleaned up data. The star itself is very active. This is what the raw data looked like. Spots were rotating into and out of view. There were flares going off on the surface of the star. There was one transit. There was another transit. There was the Spitzer Space Telescope data, which was also fairly noisy. And we developed techniques to model and subtract these effects in the photometry. So in other words, we've pioneered new techniques for this more active star, kind of like a scaled up version of activity from the activity we might see in a star like our sun. And we've been pioneering new techniques for mitigating these effects of activity in the star. And just last year, in 2021, we published the first detections of the masses of the planets. Now, this is a remarkable achievement. So this is the velocity of the star where we, in response to the planet, and we're able to put the mass and radius of these two planets. So these are two Neptune-sized worlds. And why this is remarkable is because these signals are on the order of 10 meter per second velocity change. Now that might sound not that impressive when I said the state of the art is at 1 meter per second. I went too far back. When the state of the art is 1 meter per second, shouldn't 10 meters per second be easy? Not for active stars. This star is very young. It has changes in brightness at visible wavelengths from the spots on the surface of the star of 400 meters per second. So it's like a scaled up version of a sun-like star. For a sun-like star, this effect is around 3 meters per second. So it's 100 times more active than our sun-like star. And for the first time, we've recovered signals at less than 1/10 the activity level, the false apparent motion of activity on the surface of the star. And we've been able to disentangle that activity from the true planet signals by working at near-infrared wavelengths. And so that was published last year, and this gives us hope that we can now apply these approaches to look at more quieter stars like our sun to see those faint 10 centimeter per second signals of a true Earth-like world. And so we have some telescope arrays. This is Minerva in Arizona, where we're doing Doppler spectroscopy. We've got another one in Australia called Minerva Australis. And we've also got our campus observatory, where we'll be doing light curves. And I just want to conclude by showing you JWST unfolding, which has launched. And as I mentioned earlier, it's been successfully deployed. It's really exciting. What is it going to do for exoplanets in the search for Earth 2.0? It's going to look at those habitable zone TRAPPIST-1 planets. It's going to look at TOI 700d and hopefully measure the atmospheres of those stars. If they're cloudy, we might not see very much, which is why we're hedging our bets and starting to work on this mission in the 2040s. But JWST is now fully deployed, fully focused, and it's going to do spectra of transient Earth-sized worlds orbiting M-dwarf stars, at least a couple of which are in the habitable zone. NASA is going to launch the Roman Space Telescope in the late 2020s, and it's going to push and advance our ability and technique to do direct imaging of other worlds. It won't see other Earths, but it will be able to see cold Jupiters and cold Saturn equivalents. And then, as I mentioned, NASA hopes to launch a mission in the 2040s to take a picture like this. And so this is kind of what I hope to see, a discovery of an Earth 2.0 with a mass measured by the Doppler method and the atmosphere characterized with this mission in the 2040s. We'll maybe find another Earth-like world and understand whether or not it has signs of life. So thank you, and I'll take questions.
Thank you so much, Peter. That was a great talk. And I think you have answered some questions that came in the chat already. I just see one more question that has come in from Marianne. Depending on the size of the star and mass of the planet, if the barycenter stays within the star, does this make the Doppler method not effective, or will it still give you information?
Yeah, so in the case of our own solar system, the barycenter, the center of mass of our solar system, most of the time does stay inside the sun. But it does sometimes actually have excursions outside the sun. As long as it's not at the exact center of the sun, we don't care. If the sun will still wobble around that. So it can be wobbling around a point inside the star, and we'll still see that wobble of the star. And it's a fairly indirect and obtuse method if you think about it, right? We're relying on some mathematical tricks of physics to detect, because the star is very easy to see. We get a lot, as I said, 10 billion photons for every one photon we'd get from a planet, which is very faint. By the way, to a fun analogy that is often used in this example we have here on the screen, you're here in San Jose. If I took you're in San Jose and I'm here in the DC area, and so if I took a searchlight that kind of lights up the night sky advertising some event or some sporting or commercial event, and I have a firefly next to that searchlight, seeing the light from an Earth-like world is like seeing that firefly next to the searchlight in DC from San Jose. I'll give you some like human scale analogy for what 10 billion flux contrast ratio means. So it's much easier for us to see planets indirectly by the effects that they have on their star. Nonetheless, we know that's not very satisfactory. Nothing beats seeing the planet itself. But yeah, but oftentimes they go hand in hand, because the direct imaging method will not give you the mass of the planet. It'll give you its orbit, and it can show you kind of how far away it is from the star and what its atmosphere looks like. And you can use models to estimate what its radius is, but you're not going to get a good estimate of its mass. So being able to tell the difference between a rocky world and a Neptune world, particularly a blue world, like Neptune, is going to be a fun challenge.
That's cool. I guess there is one more question. And before I get to that, I just want to quickly mention that if you want to ask your question yourself, feel free to unmute and ask the question. This is the part of the session that's interactive. It doesn't have to be all of us staying on mute and just listen to Peter talk and give his wonderful knowledge share his wonderful knowledge with us. I'm also checking the chat channel in the YouTube to see if there are any questions coming in. So jump in if I miss something in the chat on Zoom. The next question is from Stefano. Thank you, Professor Plavchan, for your real interesting lesson. I have a general question. Are world scientists collaborating or competing in the search of exoplanets? Do other countries have access to Kepler, Minerva, or do they have their other telescopes?
Well, this is a great question. And the culture of astronomy is just as important as the science of astronomy itself. And astronomy and science in general has had its problems with its culture. I imagine for those of you in the Silicon Valley area know a little bit about challenges of culture in the tech world.
Yep.
So I will say that there are approximately 3,000 professional astronomers in the United States, which works out to be about 1 for every 100,000 Americans. And there are a similar number, slightly larger number internationally. They're kind of like frenemies. Friendly competition is probably a way to put it. In the discovery of this system around AUMIC, which I found, we've been competing with a couple of teams in Europe. And that's been a bit challenging for me because I haven't been used to the competition, to be honest with you. The test mission has been a really great collaborative effort domestically and internationally. JWST is an international observatory. NASA tends to try and take credit for all of it sometimes in press articles, but in truth, it is a partnership with ESA, the European Space Agency, and one other space agency whose name is escaping me at the moment, whether it's Canadian or Japan, I forget. But we do have, unfortunately, by law, NASA is forbidden from direct one-to-one collaborations with China. And so we definitely have competition from Chinese astronomers. And in science, there is good reason to have both collaboration and competition. It's good to have competition for one of the key principles of the scientific method, which is reproducibility, which is that if your experiment can't be reproduced, then can you actually believe it actually happened? I mean, that's one of the great successes of the scientific method, is that reproducibility is inherent to what we do. Now, today, reproducibility usually comes in the form of peer review of the papers we publish and the experiments we carry out. But it's nice, actually, in the AUMIC system that another group in Europe published a paper this year, basically doing a slightly different analysis using their own data to measure the masses of the planets. And it was great to see that they found masses that were fairly similar to our own, with some differences, so we got to work out on the reasons of those differences. On the other hand, too much competition can be bad because it's not optimal use of resources. These days, astronomy is resource constrained, and NASA in general. During the Apollo era, at the peak of the Apollo missions, NASA got roughly 4 cents of every tax dollar. Today, that number is under a half of a penny of every tax dollar. Right? It's about $25 billion per year. By comparison, the U.S. military's annual budget is equal to the entire 50-year history of NASA's budget. So basically, you could afford another 50 years of NASA with 1 year's worth of military funding. So we are fairly resource constrained with what we can do. And so we have to find an optimal balance between collaboration and competition. And sometimes you want to avoid duplication of effort. Your science is better off for it. Europe and the US have often had a friendly competition. We're flying the Roman missions shown here. they're launching Euclid. We flew the TESS mission. They're going to launch Plato in a couple years. It's going to be a bigger, better version of TESS. We launched the Kepler mission, which was a bigger, better version of the Corot mission, which the Europeans launched shortly before. We launched the Spitzer Space Telescope. They launched the Herschel Space Telescope. The science cases were very similar. The capabilities of the different missions were slightly different. So there's a bit of a back and forth competition between the US and it really depends on cost. For missions like JWST, we can't afford JWST as a nation on our own. And so we have to partner internationally with the current budget allocations we've been given. But for smaller missions, we can, and so there tends to be competition. So that's, in a nutshell, kind of an answer to that question. So I will say that increasingly in the exoplanet field, we do find ourselves participating more in the era of big science. And what I mean by that is that collaborations are getting bigger, facilities are getting bigger. I mean, this is a facility like Minerva and Minerva Australis, which I'm a co-PI of. One of our key partners is Australia. It's a rate of 27-meter diameter telescopes, where we are them to feed starlight into a spectrometer to measure the velocity of a star. Another example I wanted to show. I forget now. Oh, this one. Yeah. Oh, big science. Yeah. So this is, the VLT, this is probably a $50 million project. Ground is still a lot cheaper than space. The TESS mission on itself is $150 million. The Kepler mission was $700 million a decade ago. The JWST is a $10 billion mission. So, but this is kind of like a $50 million spectrograph. It's pretty darn expensive, pretty darn complex. It requires a lot of teams contributing to it. So you have to work together because it can't give every individual professor $50 million to do their pet projects of science. So yeah, we have to compete for the limited resources that we have. That applies to telescope time too. If I want to get JWST time, I have to write a proposal, and I have a 1 in 10 chance maybe of getting time on the telescope.
Mm-hmm. Yep, that's pretty cool and very interesting. I have a follow-up question. So in terms of the exoplanets research, have you seen, or have you, I should say, I've heard sometimes that NASA's focus changes as with change in administration every few years. So has exoplanet research suffered from any of that ever?
That's a great question. So I have been a professional astronomer now for 16 years since I got my PhD. And I used to work at the NASA Exoplanet Science Institute. So I was directly part of NASA for a time prior to becoming a professor. And so I have seen administrative changes. I have seen shifts in priorities. And I can say the following. Politics has impacted our field, particularly with JWST. So JWST is a $10 billion mission. But 12 years ago, when the National Academy's Decadal Survey came out and recommended the Roman Space Telescope, it was only supposed to cost $3 billion.
Oh, wow.
When it was originally designed 20 years ago. And the cost just ballooned. And that pissed Congress off.
Mm-hmm.
And it almost feels like, as a scientist, that we as a field were penalized for that. The funding for the rest of astrophysics since 2010 has been relatively unchanged until the launch of JWST. And frankly, we are so fortunate that JWST has worked flawlessly so far. Mm-hmm. And you see all these steps here. There are over 300 deployments that had to go off flawlessly for the deployment of this telescope, and they all did. It's quite a remarkable feat of engineering. This shows NASA at its best sometimes. They over-engineer the hell out of things, and they don't tolerate risk.
Yep.
But you don't necessarily want to tolerate a lot of risk when you're spending $10 billion of taxpayer money. So true. In any event, getting back to this question about funding changes, I do feel politically, independent of party, astrophysics has suffered financially in its non-JWST budget, and now that JWST is finally launched, most of the money is already spent. Building it was the hard part. And so I'm hoping that, we'll see some better funding in the field going forward. But we don't see so much fluctuations otherwise in astrophysics. It seems to be kind of at a steady rate, and it really does just seem to be politics. We could do a lot more with double the budget. So if you want to write to your legislators and say we should do more astronomy, I mean, NASA Ames doesn't have Kepler anymore. What is it doing in astrophysics? It could use a new mission. Then write to your representatives. We are right now at the cusp of the next round of great observatories. So in 2021, the National Academies released its decadal priorities of astrophysics, which relate to this mission that I'm going to skip over, to take a picture like this in the 2040s. And this is the first in what could be a potential set of 3 or 4 great observatories, akin to the great observatories we saw in the previous generation of Spitzer, Hubble, Chandra, and Compton, NASA's previous great observatories. But they're going to cost money. And they're going to cost more money than NASA can afford. So it's either going to need an increase in NASA's astrophysics budget, or it's going to need international partnerships to make up the remainder of the costs. And I don't know how it's going to play out. That's going to be politics. Whether or not we think we have the taxpayer support to fund these things. I will say, however, that other areas of NASA science has been subject to the ebb and flow of administrative changes, particularly earth science and climate study. So invariably, right, during the Biden administration, we've seen increases, reversing cuts from the prior administration in climate science. Planetary science seems to always go up and down too, for whatever reason. Studies of objects in our solar system, that is. Heliophysics is never funded enough. They're always going at a very low level. So yeah, not so much administrative changes, but earth science definitely gets hit by that. And then in the crewed space, you've seen that there have been a lot of changes. Politics definitely have played a role in the development of the Space Launch System. And obviously what Elon Musk is doing with SpaceX has been both a boon to science and a bust for astronomy, which you can ask me about if you'd like. But you know, the commercialization of space has been going on for a long time and has really started to accelerate in the past 10 years.
Yep.
Peter, this is Kanch.
Well,
I have a question.
I see Kanch has a question, so let's get to that.
Just opening the question. So what you're looking for this, first of all, thank you for this great talk. You're seeing this, you're looking for these Earth-like planets. Quickly, can you tell like what are the next plans? You know, you're going to see this, right? You're going to make the instruments better and better, and eventually we'll find this. What's the next steps after that? Yeah,
so that's a great question. So, and I had to skip over a little bit of this due to time. So the Kepler mission taught us something pretty important, which is our best guess, estimate, and extrapolation of how many stars do we need to look at. In other words, what is the frequency of Earth-sized worlds in habitable zone locations orbiting sun-like stars? Now, in the case of Kepler, we fell a little short in sensitivity in terms of orbital period and planet size. We detected Earth-sized worlds at shorter orbital periods, and we detected bigger worlds, Neptune-sized worlds, in habitable zone orbits. But from those two measurements, we can extrapolate to Earth-sized worlds in habitable zone orbits. And essentially, we're getting numbers on the order of 20%, that roughly 1 in 5, some say 1 in 10, some say smaller, some say 50%. That's why it's an extrapolation, depends on who you ask. But we know it's not 100%, and we know it's not 0.1%. We know it's not 1% either, but it's on the order of 10 to 20% of sun-like stars have Earth-sized worlds and Halo-zone-like orbits. And so that is what we learned from Kepler over the past decade. We're still working on that data set and refining that number. And so the next question we're asking is, are we going to know which stars nearby the sun have these Earth-sized worlds amenable to imaging? That's where the Doppler technique comes in, because we can search over the next 10 years, provided we continue to develop the techniques for analysis to find these Earth-sized worlds that could be directly imaged. The transit method won't work because with a flagship mission like this, we'll only be able to look at a few dozen stars, maybe 50 to 100 tops. And so we have to pick and choose our stars very carefully. They have to be close enough that we get enough photons from that Earth-sized world so that we don't have to watch it for a year, so we can collect enough photons in a matter of days. And so the big question right now is this direct imaging telescope going to have to search for those Earth-sized worlds, or will we know when it launches which stars already have them and when and where we look? So that's what I've been working on in my research. So I've been doing simulations of the current generation of radial velocity surveys to answer that question. And we're working on it. We do believe that over the next 10 years, provided NASA funds it, or the NSF funds it, that we will be able to survey these nearby worlds and mitigate the effects of stellar activity and detect these Earth-sized worlds to be directly imaged in the 2040s. So I'd say the research right now is on that question. People are, the exoplanet field is pretty evenly divided into characterizing worlds and finding worlds. And so there's a characterizing worlds group, and they're primarily using JWST. So JWST is the thing. And for the finding worlds, the Gaia mission is about to launch. I didn't even talk about the Gaia mission. It's a European mission. It uses a new technique which detects the wobble of stars, not in velocity, but in position. And so that's called astrometry. And astrometry has never been used until recently to detect another world because it's very hard. To detect an Earth-sized world in a Halo-zone orbit around a sun-like star requires measuring a change in position of the star of less than 1/1,000,000th of 1 arc second, where 1 arc second is 1/3600th of a degree on the sky. The Gaia mission can't do that. The Gaia mission has a sensitivity maybe 100 times that. So it's going to be able to detect Jovian-sized worlds like this Jupiter here. And so it's expected to find thousands of cold Jupiters. And it's going to announce the data to detect those this summer. Kind of exciting. So some of the people are going to be focusing on that data set that's coming out this summer. But some of us are working on the Doppler method. And we're hoping that with the detection of worlds, with the Doppler method, that we're going to get that last factor of 10 in sensitivity that we need. We've all become experts in stellar astrophysics. What's going on in the atmospheres of the stars? How are the barcode of absorption lines, how are they being formed? What are the astrophysics? We know this, of course, but we're kind of rediscovering it. Because the Doppler method, prior to about 5 years ago, we just treated the spectrum of a star as a one-dimensional time series. For all we cared, it could have been stock price, right? But we're looking at that motion back and forth, and we didn't care in wavelength, and we didn't care whether or not any individual absorption line was due to, say, iron in the atmosphere of that star. But now we do care. And so we're trying to disentangle the effects of active regions on the star. So I say a large portion of the exoplanet field is focused there. The test mission is still going, and the test mission is finding amazing things with the transit method. It is finding lots of young worlds, like the AU system that I talked about, and that tells us all about planet formation. So I mentioned at the beginning of my talk, we have all these compact multi-planet systems, and how did they get there? Well, if we start finding them around young planetary systems, then that gives us a clue. And then finally, the direct imaging community is still very busy. They've searched very hard for finding young Jovian planets around nearby warm stars, and they found a handful of about a dozen of them. And they are pushing the limits of the analysis techniques and the adaptive optics technology and the coronagraphy to the limit on the ground in preparation of the launch of the Roman Space Telescope in the late 2020s. There's also tons of work on exoplanet demographics coming from the Roman mission using the microlensing technique. I didn't talk about the microlensing technique. It's not obscure, but it's one you don't normally hear about it, but it relies on the fact of the Einstein's theory of general relativity. If you have two stars pass in front of each other where they're very far apart, the closer star acts like a magnifying lens of the faraway star, and you can use the amplification and brightness to detect other worlds. And the Roman mission is going to find thousands of cold Neptunes this way, and it's going to teach us a lot about, I mean, maybe even some Earth-sized worlds. It's going to tell us a lot about the demographics of planets at the outer edges of solar systems, where we really don't have a lot of information to date. We have no idea really how common Neptune-sized planets are at Neptune distances from our sun. So yeah, there's a lot going on. The search for Earth 2.0 is only a small piece of the study of exoplanets. It's a huge field. It's growing rapidly. It's kind of eating astronomy, as it were. And a lot has changed over the past 25 years due to really advances in technique and precision and computation.
I'm muted. I did not realize that. Sorry about that. It is getting really late for Peter, so we should probably let him wrap up. Thank you once again for your time, Peter. It was really great having you. And the talk is recorded, so you can always go back to the YouTube link that I have shared. Any of you, if you would like to watch it again. And we will wrap it up here. And thank you, everyone, for joining. And let me know if you have any feedback. I'm reachable. My email is on the website, so let me know.
Thank you all for having me.
Yep.
Oh, great. Thanks a lot.
Yep. Thank you.
Bye-bye.
Good night.